Eleanor, get back in your seat. Class is started. Good morning, everybody. Welcome back to Galwan Theory. I'm just teasing.
Okay. I have to cancel the order because there's no applied math club today.
Hope y'all are having a good day so far. Plan for today is we're going to talk about solvable groups and then solvability by radicals. Today I've got a whole packet on radicals. We're going to get radicalized. Great.
Woo!
Got usual office hours this afternoon, 1 to 2, as well as tomorrow from 11 to noon and 1 to 2. Homework? No new homework. Don't forget you have a homework set due by the end of today, though. So make sure I have it by the time I come in tomorrow morning. Oh yeah, there's dogs. Chase is going on outside here.
Dog.
So yeah, at this point there's not going to be any more homeworks. All that's left after today is the final. And I'll send that out later this week. Don't be surprised if that means Thursday or Friday. Because it's probably not going to be today. But you'll have a week to work on it. Same rules, midterm, you can work with a partner, etc., etc. It'll be fun. It'll mostly be focused on the more recent stuff since the midterm. I might put like 1 or 2 questions about early stuff, but only if it's like relevant to the stuff we've been doing more recently. So expect a lot of field extensions and less stuff relating to Euclidean domains, PIDs, etc.
I was just going to ask if it's going to be like a week to work on it.
Yeah, you'll have a week. Yeah, you'll have like a weekish to work on it. Depends on when I get it out. I'll say when the due date is, but it'll be at least like it'll probably be like 7 or 8 days. Any other questions or comments? We're getting started for today. Oh, nice of you to rejoin us. All right. A chemist, an engineer, and a mathematician stumbled across a pile of beer cans, and boy, are they thirsty. Unfortunately, they're the old-fashioned cans that don't have a little tab that makes them easy to open. So one of them proposes that they split up and go find can openers. The chemist goes to his lab and concocts a special chemical that dissolves the top of the can in an instant, but then immediately evaporates, that the beer inside is not affected. The engineer goes back to her workshop and creates a new hyper can opener that can open 25 cans per second. So chemists and physicists are convinced that they solved the problem, so they go back to the pile of cans to find the mathematician finishing off the last can of beer. They ask the mathematician, wait, how did you get in there? Mathematician said, oh, that was easy. I just assumed that they were all open and started drinking. Indeed. All right, and with that, let's hop back to it. So last class, we started talking about, what's that?
I was wondering if it was going to be defining the inside without.
Yeah. Oh yeah, I just defined myself. And suddenly all of spaces, except for in the can, is filled with beer. Oh gosh. Okay, so last time we started introducing this concept of solvable groups. Or a group is solvable if we can kind of construct a sequence of subgroups. We call this a tower of subgroups, such that for each term here, each subgroup is a normal subgroup of the next one. And also, each quotient of consecutive subgroups ends up being either abelian or cyclic, depending on your definition. And we also proved towards the end of class last time that if G is a solvable group and H is a subgroup of G, then H also has to be solvable. We also proved the second isomorphism theorem, but we're not really going to be using that today. And so what I want to do today is talk a little bit more about solvable groups, give an example of a class of subgroups that is very much not solvable, then talk about how does that relate to something called solvability by radicals, and with the goal that by Thursday we'll be ready to tackle insolvability of the quintic. Woot, woot. Questions or comments before we get going with the new stuff? So, last time we actually showed with examples that S3 and S4 are both solvable groups. We actually constructed a tower of subgroups for each of these that satisfied the conditions we wanted. Turns out S5 and up are not solvable. And first half of today's class is going to be proving that. That for S5, S6, etc., you cannot find a sequence of subgroups that do this stuff. But first things first. First thing we're going to do is we're going to prove a lemma for a theorem. So I'll say the theorem first. I forgot to actually put the lemma in the packet properly. But the theorem we're going to be looking at next is for all n greater than 5, or equal to 5, A sub n is a simple group. Meaning it has no, I say normal subgroups. I should say no non-trivial proper normal subgroups.
Lincoln's not here today to complain about.
Good for him. So what does that mean? Well, I have to include proper and non-trivial because any group has at least, any non-trivial group always has at least two normal subgroups. Namely, the trivial subgroup is always a normal subgroup of the whole thing, and the whole thing is always a normal subgroup of the whole thing. That's just kind of trivial to prove. But it turns out we say that a simple group is one that doesn't have any other normal subgroups. And I claim A sub n gives us such an example. So, first things first, we're going to have a little lemma here. And our lemma is going to say for all n greater than or equal to 3, A sub n is generated by all 3 cycles. And S sub n.
All meaning like by any single one or?
By the set of all,
Okay.
let's say. And yes, that's not a minimal generating set. You don't need all of them, but it turns out if you have all the 3 cycles, then that'll give you A sub n, it turns out. So, question, what is A sub n? I think we mentioned this last time, but haven't really done much with it. We said S sub n is the permutations of the set from 1 to n. Which we denote with cycle notation. What is A sub n, or the alternating group on n elements? Eleanor, is that a hand?
Sure.
Answer.
It's the set of all elements in S sub n that can be decomposed into an odd number of cycles? Or is it even number or something like this? It's even, yeah.
A sub n is the permutations, it is the elements in S sub n that can be written as an even product of 2 cycles. I think so. Odd product doesn't give you a sub. Odd product isn't even closed.
Yeah.
Because if you take 2 odd permutations, multiply them together, well, you get an odd number of 2 cycles plus an odd number of 2 cycles, give you an even number of 2 cycles. That helps a lot. So for instance, if S3 and A3, if we want to look at what's the permutations of S3 that can be written as an even number of 2 cycles? Isaac?
1, 2, 3, and 1, 3, 2.
Yeah. 1, 2, 3, which we can write as being 1, 2 times 2, 3. We can write 1, 3, 2 as 1, 3 times 3, 2.
And 1.
And the identity, which you can write as take any 2 cycle and do it twice. But individual 2 cycles in S3 are considered odd permutations because they're written with an odd number of 2 cycles. So they would not be included. So I claim the set of all 3 cycles in Sn is going to generate A sub n. So what does that mean? What does that mean? Well, first thing I'm going to say for proof of our lemma is that I hope everyone believes me when I say that AN is generated by all elements of the form A, B, C, D. In other words, any element in A sub n can be written as a product of things of this form. Alright, because you need an even number of 2 cycles, so you can always write it as the product of some number of collections of 2 cycles multiplied together. Will give you everything in A sub n. So basically we just need to check, can anything of this form be written in 3 cycle form? Well, if AB is equal to CD, then how can we write this as a product of things? We can write this as, that's just going to give us the identity element. How can we write the identity element as a product of, say, 3 cycles?
Any 3 cycle, do it 3 times.
Yeah, pick any 3 cycle, do it 3 times. I don't know, 1, 2, 3, cubed, done. So things of this, so if AB is equal to CD, then things of this form can be written in using a product of 3 cycles. How about if A is, how did I write this? If A equals D, but B is not equal to C, so we have something of the form AB times AC. What's that going to give us?
A 3 cycle.
What?
A 3 cycle?
A 3 cycle?
It should give you a 3 cycle.
All right, what 3 cycle?
AC.
Well, let's see. A will map to C, which doesn't map anywhere.
Yeah.
C will map to A, which maps to B.
Yeah.
B maps to A. Yeah, that can be written as a 3 cycle. Several different ways, in fact. And finally, if A, B, C, if the 2 cycles are completely disjoint, so if all are distinct, I claim we can still write this using 3 cycles. How? I'm going to be sneaky about it. I'm going to write this as, I'm going to sneak in an AC in the middle here. Because what's AC times itself?
The identity.
And that's just the, yeah. Any 2 cycle times itself is the identity, so we can sneak that in the middle there.
AC looks familiar.
Wha-pow, wha-pow. What does ABAC equal, Parker?
It equals ACB.
Hey, we just did that, didn't we?
That's so familiar.
ABAC is ACB. How about this other one, Matthew?
No, I mean, I'm sorry, so you put in an A in the right side, so that's gonna go to C, so A to C, and then a C from the right side, that's just gonna go to D.
And what's D gonna go to?
D's gonna go to C, which is gonna go to A, background again.
Hey, it's a product of 3 cycles. Thus, A sub n can be generated by 3 cycles. In other words, if all of your 3 cycles are in some subgroup of S sub n, if all 3 cycles are sufficient to give you all of A n if you take products of them, in other words. Any questions or comments about that? Groovy. All right, so let's prove our theorem then, that A sub n is simple. So first of all, we're going to take a note. This is going to be a, we're going to start by letting n be a normal subgroup that's non-trivial in A sub n. with a sub n not equal to the identity. Then I claim every 3 cycle and in a sub n must lie inside of n. I claim that if n is a normal subgroup of a sub n that's non-trivial, then it has to contain every single 3 cycle. Why is that? Stay tuned to find out.
Oh, sorry.
Eleanor?
Do you mean that n is not the trivial? You said n.
Oh, yeah. Well, I mean, a sub n is non-trivial because we're assuming n is
Yeah.
at least 5.
Yeah.
So this is going to be a 5 let's say a question. Well, if n contains every single 3 cycle, and it's a subgroup of a sub n, what can we conclude about n?
It's a sub n.
Yeah, by our lemma, if it contains all the 3 cycles, well, since the 3 cycles all generate a sub n, and if n's a subgroup of that with all the 3 cycles, the only possibility is that by our lemma,
So in fact, we're not proving this right now, we're proving it on the exams.
exactly. I will make a comment. This result is actually in the book. When the thing I'm going to give you on the final isn't this proof exactly, it's going to be a slightly altered version of it.
Wish I'd bought the book, maybe.
Say what? Oh, if only Emily Rose had a copy of the book. Don't worry, you're not going to necessarily.
Yeah, online. Oh.
Emily Rose, you're not going to need the book to do this. But I mean, well, you shouldn't need the book the way I have it planned.
I haven't needed the book all semester. I'm just really curious about this example and I want to read it.
Well, I'll tell you, it's on pages 166 to 167 in the book. It's a bit long and tedious to prove this in the general case, which is why we're not doing it in class. But we are going to look at. I'll just tell you, I have a plan, so we're going to do it for for A5 specifically. We're going to go through and show this.
I think if you have one recycle, you have all of them back contribution.
Spoilers. But yeah, you're gonna do this. Yeah, it turns out this is in the book. It's long and tedious. I don't feel like proving it, but turns out doing it for A5. But turns out there's a fun little argument you can do to do it for A5 that's a little bit different. So that's gonna be on the final. Sound good? Okay. So with that in mind, I claim S sub n is not solvable for n greater than or equal to 5.
Why does this fall apart when n is less than? I mean, obviously we showed that S sub n was solvable for lower, so it does. But why? What changes at 5?
Not enough degrees of freedom. Or, well, what changes at 5 is, I should say, sufficient degrees of freedom.
Ha!
Messy, complicated, don't feel like getting into it now. Read your textbook. So, corollary. For n greater than or equal to 5, S sub n is not solvable. So, how are we going to prove this? Well, if S sub n was solvable, what else would have to be solvable?
Basically. Every subgroup.
Subgroups, like AN, for instance. We're going to suppose S sub n is solvable. And then since, I think technically we only proved this for normal subgroups, but A sub n is a normal subgroup because it is index 2, so that's fine here. A sub n must be solvable. with subgroup tower. Trivial equals, we'll call it G naught less than or equal to G1, less than or equal to less than or equal to G sub n minus 1, less than or equal to A sub n, where all of these are normal subgroups, I should say. But here's the problem. How many normal subgroups does A sub n have for n greater than or equal to 5, according to what we just proved? Eleanor? What does this mean?
Well, because it has itself and then the trivial.
Yeah. We have a problem. A sub n doesn't have any normal subgroups, so that kind of forces, since A sub n is simple, this kind of forces a bunch of equalities and our tower to evolve into of the form is a normal subgroup of A sub n. Makes everybody on board with that? I mean, technically we could have some of these terms are just equal to A sub n and just saying A sub n is a normal subgroup of itself. But if we kind of trim out the fat, where we cut off the repeat terms in the middle, so to speak, eventually our tower devolves into just that.
Take away the equal to bit and just say,
Well, yeah, at that point it's not equal to anymore, but I include that because I'm used to deal with it. But what do we need to know about this?
what happened to the subgroup side?
What happened to what subgroups then? What do you
It doesn't matter, it just looks,
like this? Oh,
yeah.
is that better?
Yes.
Everyone's a critic. Alright, so what needs to be true about then Emily Rose A sub n mod the trivial subgroup?
It needs to be abelian.
Uh-huh. Is that abelian? Well, this is isomorphic to just A sub n by itself. And A sub n is very much not abelian for n greater than or equal to 3. As for instance, you could just take 1, 2, 3 times, I don't know, 2, 3, 4, which gives what? 1, 2, 3, 4. But if you take 2, 3, 4 times 1, 2, 3, you get what? 1 maps to 3, which maps back to 1, and then 2 maps to 3 maps to 4, which maps to 2. Contradicting the solvability of A sub n. All right, questions or comments or concerns? Did I do that right? Oh, yeah, I did that. Okay, good, I did that right. I know how to do products in SM. So, S sub 3 is solvable, S sub 4 is solvable, S sub 5 and up, not solvable. I wonder if that has something to do with the quintic being solvable with radicals. Who knows?
We'll never know.
I don't know. Certainly not the next packet. Actually, we won't do the packet after this one.
Well,
So-
then it won't be.
That's kind of an overview of what I wanted to say about solvable groups for now. Mainly the result I wanted to get out of this packet was this one right here, that S sub n is solvable for n up to 4, but not beyond 5. So with that, we're going to talk about something a little bit different. We're going to talk about solvability via radicals and radical extensions.
That's
They're
pretty.
totally gnarly though. Shredding some mad ways.
What?
That's my attempt
I
at
think I may
bad
have
Beach
missed
Boy
some.
California lingo.
Shredding some mad waves. Chaw, dude. Saw, my guy.
All right, so what's a radical extension? Well, a radical extension is one where it's basically made up of a sequence of simple extensions where you're taking where you're including radicals of things. Jonah, quit hogging the packets. So we're gonna say
An extension that doesn't listen to the man.
it's an extension that sticks up for itself. Don't take no one. Don't take the chicks' names. Eat chicks' ass. Anyways, we're gonna say L over K is a radical extension.
We're radicalizing buffers.
If there exists a sequence of field extensions, K equal to L naught, which is a subfield of L1, which is a subfield of which is a subfield of L sub n, which is equal to L, where for each I, L sub I plus 1 is equal to I sub I, L sub I plus 1 is equal to L sub I, joined alpha sub I. For some alpha sub I, a root of some f sub I of x, an element in L sub I of x, of the form x to the n sub I minus c sub I. Whew. Long definition, but essentially it means you can get L over K as a radical extension if you can get from K to L by joining nth roots. So that are roots of some polynomial of this form, i.e. so that alpha sub I is an nth root of c sub I, in other words. If you can keep extending by some nth root, eventually to get from K to L, we call that extension gnarly. I mean, so let's do an example. Let's say our base field is, I don't know, Q. And I wanted to find some element alpha, where alpha is going to be the cube root of 1 plus square root of 5 minus 8 root 2, root 1 plus root 7. You know, that's a nice number. And our goal is to create a radical extension of K in which this thing lives.
I don't want to.
Oh, you big baby, it's not that hard. What?
I'm thinking, and I think that the cube root of 1 plus the square root of 5 is probably a root of.
Well, let's start with this. L0 is going to be our cube. L1, we're going to take Q and join something to it. How about square root of 5? Is that a root? Is that a root of some polynomial over Q of this form? Elmore, give me a polynomial.
X squared minus 5.
Yeah, we're joining a root of x squared minus 5. Okay, now to get from L1 to an L2, we're going to take L1 and join something else. How about we take L1 and, I don't know, what else do you want to join? Matthew?
Root 7.
Square root of 7? Okay. Matthew, can you give me a polynomial over L1 and L1 of this form for which square root of 7 is a root?
I'd probably say,
Hint, you don't have to use square root of 5.
yeah, so it'd be like x squared minus 7.
Yeah, that's a polynomial of this form that lies in Q adjoined root 5. Yeah, we can adjoin root 7 to L1 and get an L2. All right, let's keep going. What do we want to adjoin next?
Square root of 2.
Square root of 2. Okay, can you give me a polynomial in L2, Emily Rose, of which, for which square root of 2 is a root?
X squared minus 2.
X squared minus 2. Neato burrito. All right, let's move over here. All right, that still doesn't give us all of this. What else do we need to adjoin?
That cube root is still presenting us with a problem,
And the
so,
others would be. Yeah.
and the other, yeah, so,
Cube root of 1 plus the square root of 5.
I'm, well, I was.
Okay. Can you give me a polynomial in L over L3 for which this thing is a root? Jonah.
X cubed minus the cube root of 1 plus the square root of 5.
X cubed minus,
Sorry, minus 1, yeah.
like that.
Yeah.
I like it. Yeah. Cube root of 1 plus square root of 5 is certainly a root of this. If you cube it and subtract away 1 plus square root of 5, you'll get 0. How do we know this is a polynomial over L3? Well, because anything in L1 is a polynomial in L3, and this is a polynomial over L1, therefore it's a polynomial in L3. So yeah, that'll give us, okay, that's still good for making us a radical extension. Almost done. I think we can do it with one more. Isaac, what would you like to adjoin next?
Square root of 1 plus square root of 7.
Square root of 1 plus square root of 7.
Do x squared minus 1, you put the parentheses there, plus square root of 7.
Or x squared minus 1 minus square root of 7 if you want to distribute the minus sign. I like minus and then put the c sub I in parentheses to indicate this is a single element from the base
Yeah,
field.
yeah.
But, yeah. And then alpha is an element in L5, where L5 over Q is in fact radical. So radical extension ultimately just comes down to you get from one to the other by adjoining roots of things. And radical, you think radical like radical 4, that's the square root of 4. Radical just means roots. Yeah, man.
Is this like basically though the same thing as just saying like Q and then just like listing all these out in like commas?
Essentially, yeah. Yeah, we could also say, for instance, this. Yeah, and I think we even had some result back when we first did field extensions that essentially told us it worked that way. Yeah, we could essentially say L5 is just Q adjoined square root of 5, square root of 7, square root of 2, square root of 1 plus square root of 7, cube root of 1 plus square root of 5. It does end up being equal to that. But you kind of have to be careful in the order in which you're writing things out. Because in order for each thing to be an nth root of something that comes in the field before it, you already need to have, for instance, square root of 7 in order to be able to do this. Because if square root of 7 wasn't an element in L4, this would not work. Because this would not be a root of something of this form if we didn't already have square root of 7 to work with. Or similarly, for L4 over L3 wouldn't work because if we didn't already have square root of 5 as an element in L3. Jonah?
And C would still be a radical extension, right? Even though it doesn't have anything, even though at least we wouldn't ordinarily write
C would be a radical extension of what? Q?
cubed, yeah.
I don't know, can we?
Or no, I guess it would be a radical extension of R, I guess.
C would certainly be a radical extension of R, because you could just adjoin I, which is a root of x squared plus 1.
Yeah.
Let me ask you this.
I mean, Q joined I would be.
a radical extension of Q. How about this? Is that a radical extension, Jonah? Why not?
I think so.
You think so?
Any irrational number we want can be, it's just x to the 1 minus that irrational number.
But it needs to be in.
Oh, I didn't know I had to do less than infinity. Well, in that case, then no.
Otherwise, we're not gonna get transcendental numbers.
Even then, transcendental numbers will be an issue for us.
I thought about that with the infinite.
Yeah. No matter how much you try to join, you're going to have trouble getting numbers like pi and e in there.
I don't know if you need to imply that m has to be less than infinity, because if you say, because it has to eventually equal L, right? It's not like it's a limit thing. You have to make it equal to L.
Technically, you're right. No, technically, you're right. You could sort of do like a sort of weird limit of field extensions. That gets messy and into stuff I don't want to get into.
So would a strategy for finding what to adjoin to your base field would be to start from the most embedded radical?
If I were to give you a question like this, yes, I would say so. Okay. Yeah. I'll be honest, when I did this in my notes, what I adjoined was I first adjoined square root of 5, and then the next thing I adjoined was cube root of 1 plus square root of 5. Because all that we need is that this comes before this. And then I think I did square root of 7, then square root of 1 plus square root of 7, and then square root of 2 was my last thing I adjoined.
You did the depth first.
Yeah, the exact order doesn't necessarily matter, but you do kind of need innermost things before you do outer things, if that makes sense. Yeah. What's important is that your polynomial has to be lie in the appropriate polynomial ring and have the appropriate form over said polynomial ring. In other words, you're just adjoining the nth root of something that you already have. Any questions or comments or concerns related to this? Yeah, this would be an example of one that's not radical because here's another one. The algebraic numbers over the rationals. You can't do it with finite limit. It's too big.
Well, for one thing, there's infinite primes, so you're going to have an infinite number of square roots needing adjoining.
That's a problem. Indeed. Any other questions or comments? Yeah. This does give us an example of an extension that is algebraic but not radical.
What about the irrational?
The rationals are not a subfield of the irrationals. They're not a subset of the irrationals, and the irrationals also aren't a field.
Right. Never mind.
They kind of need this nice thing, you know, that's called closure.
Right.
But Q is closed. Yeah, I don't know. It's the same reason, Eleanor, is why like A sub n forms a subgroup, but the odd permutations don't.
Oh, right.
Odd plus odd is not, even plus even is even, odd plus odd is not odd. Similarly, rational plus rational is necessarily rational. Irrational plus irrational may or may not be rational. Or irrational.
Reason that Q is closed or isn't closed.
Well, it's not closed in real houses, but it's closed as.
Well,
Right.
well, okay, that's a different definition of closed.
Yes.
Closed under an operation
Yes.
versus closed under a topology.
Yes. That's.
Okay, yeah, sorry. I should be careful with when I say closed. So let's say this definition: a polynomial over K. We're going to call solvable by radicals. Wabam. If there exists a splitting field for f of x. Oh, we do. Contained in a radical extension of K. Notice that we're not saying the splitting field itself has to be a radical extension. We just have to say a splitting field is some subfield of a radical extension. What's that?
You can go up and then down.
Yeah, you can get weird stuff happening. So for instance, what's a nice example of a polynomial that's solvable by radicals? Oh, I know. How about f of x equals x to the fifth plus x to the fourth minus x cubed minus 2x squared minus 2x. I claim that this is a polynomial that is solvable by radicals. But Dr. Herschel, it's degree 5. I thought you said degree 5 couldn't be solved.
It's secretly degree 4 though.
It's, well, when we say
Oh.
you can't necessarily solve the quintic with radicals, what we mean is you can't do all quintic polynomials with radicals. You can certainly do some.
So this one you could just factor an x out and split like a quarter.
X
X to the fifth minus 1 would be 1. X to the fifth would be an even easier one. Sorry, what?
No, sorry.
So let's factor this thing. See what we need to adjoin. Oh, anybody have a factor that they want to take out of this?
X.
Yep. And then this thing isn't super easy to factor after this. So I'll just give you it's x squared minus 2 times x squared plus x plus 1. Say what?
I wanted to use the quartic form.
I did not want to use the quartic formula. You go right ahead and use that and do that if you want to.
It's so easy to memorize.
We'll see you tomorrow.
Yeah.
Parker should have
See you next semester, more like. Yeah.
We work with much larger patients.
All right. So I mean, unless you do it on computer, but what do we need in order to add to Q in order to get a splitting field?
At the very least, the square root of 2.
Yeah. Well, we need square root of 2.
And the-
Also negative square root of 2, but you get that with square root of 2 for
And the
free.
third root's of unity.
And third roots of unity. Yeah, because this thing has roots of e to the 2 pi I over 3 and e to the 4 pi I over 3. It'll stick with atomic polynomials. So, can we find a splitting field that'll do that? That's contained in some radical extension? Or perhaps, dare I say, even show that the splitting field is a radical extension?
And we can just write the splitting field as Q adjoined root 2 and e to the 2 pi over 3, right?
Yeah, you can certainly do that.
Because e to the 2 pi over 3 squared is
All right, so let's find a radical extension of Q that contains these things. Anybody have something they want to adjoin to Q to start with? Andrew?
3.
Root 3?
Okay, I root 3.
I root 3. Okay. I see you want to do it the slightly more complicated way. I was just going to join the
Wait, where did we get
No, you know what? I'm not doing that. And yes, that does work, Andrew, but that just fits.
But the numbers are so much nicer. Even if I
How
did
do you
use.
get
Where did that get invented from?
Yeah. Where did
Where
that
did you
go
pop
from?
that out?
It came from if you.
You should show us in great detail.
Is it
All I'm saying is abstract algebra pre-radic.
plus I root 3 over 2?
So if you have I root 3, you necessarily get this, which necessarily gives you e to the 2 pi I over 3.
However,
What?
the problem that I came up with the homework and the reason that I used I roots of unity is that is not the root of an easy equation. Is it? No, x squared plus 3. No, I meant I root 3. X
Oh, just
squared
I
plus
root.
3.
I root 3. X squared plus
6?
plus 3, I believe.
Is it plus 3? But no?
Yeah, because you square and you had a negative number.
Yes, but. Oh. Okay. I'm just being stupid. Moving on.
Plus or minus root 3 are roots of x squared minus 3, but I root 3 needs
No, I got the plus. I was just like, wait, but what about dividing by 2? But I don't have to divide by 2.
depends on how you want to do it. Point is, how about we just adjoin e to the 2 pi I over 3,
I like that idea.
And what's e to the 2 pi over 3 a root of?
X cubed minus 1.
Yeah, we can't use x squared plus x plus 1 here because that doesn't have the proper form for a radical extension of x to the n minus something.
How would you possibly know it's a root of x?
But we can write this as being a root of x cubed minus 1, which totally works for your radical extensions. All right. Anybody have a proposed root that we can tack on to L1? Eleanor?
Square root of 2.
Square root of 2. What's square root of 2 a root of?
X squared minus 2.
And wouldn't you know it, that gives us everything we need and is a radical extension. Turns out our splitting field in this case, if we can write as being a radical extension itself, is a splitting field for f of x and is a radical extension of q and thus f of x is solvable by radicals. Well, specifically those, although as Andrew pointed out, there's other ways of getting there.
The goofy way, yeah.
This way's not really goofy. It's just like it's just noting that if you have I root 3, you have things like I root 3 over 2, and that plus things in Q. It's not really that goofy. It's just slightly more complicated. Just doing it like this.
Marginally so anyway.
It
Marginal.
also doesn't give you the splitting field.
Say what?
It also does not give you the splitting field.
What? How is this what?
It doesn't give you the splitting field, right? Or no, maybe it does.
It does.
It does.
It does.
Yeah, okay.
Yeah, it's just that you didn't have to like go through and add another root that's in Q already to do it.
It's just a slightly messier looking way of getting there. All right. So what's an example of a polynomial that is not solvable by radicals?
I might be misremembering, but what about x to the 5th minus x plus 1?
X to the 5th minus x plus 1?
Or I might be thinking of the wrong coefficients, but that might be it.
How do you know such a thing?
I looked it up.
Oh! Lazy bum!
What if we had x to the 5th plus x to the 4th plus x to the 3rd plus x squared plus 1, x plus 1?
Nope, that one's
That was
solvable.
very solvable, Eleanor.
Oh wait, never mind. What if
I
you
think we've literally seen that exact one in like the homework.
And solved it by radicals.
Well, hold on. Well, it's actually very difficult to come up with something from the definition and say this thing is not solvable. I make fun of Parker, but I honestly did the same thing.
Yeah.
Here's the one I came up with. X to the 5th minus 20x plus 6, because that one was in the book.
I like the simple one.
Minus x plus 1, I mean.
Try the simple one, see where it goes.
Moral of the story is, hint, it needs to be degree 5 or higher.
That'll do it.
Well, yeah, you're doing. Yeah, at least over Q. If you really want to have a fun time, try doing this for your base field, something like Z mod PZ.
Oh, no, thank you.
No thanks. Lucky you're not going to have to do that on the final.
I'm so sorry.
So here's a nice theorem that kind of tells us a lot about when this happens. We're going to let K be a field. Characteristic 0. I'm not going to make you do one Z mod PZ on the final. At least not one like this, because you need characteristic 0 for the nice results to happen.
Yeah.
You can literally just say anything will be on the final, we'll all freak out.
On the final, I'm going to give you a question where you're going to be looking at if Q adjoins square root of 2 is a simple extension.
No! You didn't teach us that.
Turns out a polynomial is solvable by radicals if its Galois group is solvable.
Oh, nice.
That makes sense.
I thought these would.
So, f of x be a polynomial with a Galois group of f solvable. Galois group of F, meaning like you take a splitting field extension of F over K, and then you look at the automorphisms of that splitting field extension and show that that's a solvable group. Then f of x is solvable by radicals. Boom.
Is this a, if and only if?
Oh, stay tuned.
That's gonna be on the fire.
No, that's not going to be on the file. I don't want to prove that. A, I don't want to prove that. B, it's in the textbook. So, or when I say proof, I meant grade. I don't want to grade that, and it's in the textbook.
Well, I mean, you would have to prove it because so you need the answer, but
I mean, hypothetically.
Spoiler alert, flip forward a couple pages in the packet and you can see the answer for yourself right now. It turns out that the reverse direction O is much harder, and I don't want to actually do that one in class.
We're gonna do it on the fly.
I mean, if you really want me to, I can.
don't you dare, Parker.
Can you put things on the final just for Parker? Have to give him a separate.
I refuse. But as tempted as I am to say yes, I refuse.
I don't know why you're so nice to me.
It's less being nice to you and more being nice to myself. Alright, so
I like Tech as a bad guy.
Galois group solvable, fx is solvable by radicals. Hence why the word solvable is appearing in what seems like two very different contexts here. So, let's prove this. We're going to let L be a splitting field. Actually, I want to say this first or say the lemma first. We're going to say the lemma first. So first of all, here's the lemma. Okay, this is before the proof.
The limit in the packet or no?
No.
Okay.
Characteristic of k is 0, and x to the m minus 1 splits completely over k. And if L is a cyclic extension of k, then L is a splitting field for some polynomial of the form x to the m minus k over k. Okay. Question. What's a cyclic extension? Hint, cyclic has something to do with groups. Isaac?
Would it be by the Galois correspondence, it corresponds to something that's cyclic? Or is everything?
I mean, you don't even need the Galois correspondence necessarily. L cyclic, L over K being cyclic just means the Galois group of L over K is a cyclic group.
Okay.
Cyclic meaning can be generated by a single element. So in other words, if you have an extension of K that happens to be cyclic, and if x to the m minus 1 splits completely over K, then L has to be a splitting field for some polynomial of the same degree. We are not going to prove this one. It's another one of these. It's in the book. This is kind of one of these results that leads up to the, one of the 20 or so lemmas that lead up to a proof of the Galois correspondence theorem, fundamental theorem of Galois theory, which yes, I realize we haven't stated in full yet, but we will.
In this packet?
No. It's not the most exciting result. And look, we have less than 3 classes to go at this point. I would rather prove more interesting things. Are we all okay with that? We're going to use this result though. All right. Now, to the actual proof of the theorem, not the lemma. So really, what I'm really interested in doing is seeing how did this idea of solvable groups tie in with solvable by radical extensions. If it makes you feel better, Emily Rose, we are going to use the Galois correspondence theorem at one point in this proof. All right, so here's our proof. Hi Lydia, how are you doing? You following along? Having a little bit of trouble, but doing okay? Glad to hear it. Let me know if you have any questions. We're going to let L be a splitting field. Of f of x over k. Problem is, we don't just need a splitting field of f of x over k. Say what? Well, with the Galois group solvable, we don't just need that the Galois group solvable. We also need, we're going to need this result. So we're going to have to adjoin some things to this, which we'll do in a second. First thing we're going to do is we're going to let m be the size of the Galois group. In other words, it's the order of the Galois group, the number of automorphisms of L that fix k. And we're going to suppose that our Galois group is solvable. Ready for a fun lattice? So we're going to have L over K, which I'm going to very suggestively draw like this. But we also don't want to just have L be a splitting field over K. We want to have a splitting field over K where not only does f of x split completely, but we also want x to be m minus 1 to split completely. So what we're additionally going to do is we're going to let E be a splitting field over K of x to the m minus 1, n being the order of our Galois group. And m be a splitting field for f of x over E. Oh, actually I screwed this up already. So what happens is we're going to have some E over here. It may be L, it may not be L. Maybe L is contained in E, maybe E is contained in L, but we don't necessarily know. Depends on what f of x is. Both of these are going to somehow have a copy, are going to be contained in M, or at least be isomorphic to some subfield of M. And in the middle, we're going to be looking at L intersect E. And it's just going to contain K. There's our lattice diagram. Here's a fun result. Then M can be treated as an extension of L with the Galois group of M over E. Turns out the Galois group of M over E is going to be isomorphic to the Galois group of L over L intersect E.
Little m. No, big M can be treated.
Big N, yes.
What does that?
Big N.
What
Top
does that mean? Treated as an extension of L, since it's not.
Technically, L, yeah. Technically, L doesn't have to be a subfield of M. It depends on how we're doing our extensions. But L does have to be isomorphic to some subfield of M, and so we're treating M as an extension of L in that regard.
Yeah.
As and M contains a subfield that is isomorphic to L. Maybe L is actually a subfield of M, maybe not. It kind of depends on how we're doing all of these extensions.
Yeah.
Gets a bit messy. For the sake of argument, though, we're going to want to treat L as being like a subfield of M. Yeah, turns out the Galois group of M over E is going to be isomorphic to the Galois group of L over L intersect E. Does this look familiar to anyone? Andrew?
That reminds me of Sid.
Kind of reminds me of SIT as well. Turns out this doesn't follow exactly from SIT, but it's from a SIT-ish result, if that makes any sense, which I don't want to take the time to prove. But I will add as a parenthetical, this is somewhat similar to the second isomorphism theorem from last time. We're taking L mod, L intersect something else. That's sort of a SIT-ish thing to do. Only a SIT deals in absolutes. And again, this result is in the book, which is just, but it's something we're going to use once and kind of forget about in the interest of time. If we had like 2 or 3 more weeks, we'd go through and actually prove all of these results hopefully. Okay, then, all right, let me ask you this. What's the relationship between this thing and that thing? Automorphisms of L that fix L intersect E, and automorphisms of L that fix K.
One divides the other.
Divide? What does it mean for a group to divide another group?
The order of the extension
It does.
It contains.
divides
Okay, more what can we say in addition to just the order of one divides the order of the other?
Doesn't the Galois extension or Galois group of L over L intersect E contain the Galois group of L over K?
Nope.
Really?
This does not contain that.
Oh no. What? The other way around?
Yeah, because if you fix L intersect E, K is contained in L intersect E. So if you fix L intersect E, you necessarily fix all of K.
Yeah.
Yeah,
But if you fix K, do you necessarily fix L intersect E?
no, that was
No,
what
that's
she
why I
said.
It contains L over K.
This is what I was going for.
What?
Isn't it the other
No.
way around?
That's
So what?
It's
no, you was right.
What?
I'm confused.
Someone
I'm
convince me
confused.
that I'm right or wrong. Now I'm questioning myself. Okay, if you fix L intersect E, then you necessarily fix K. So any element in this thing is a phi going from L to L,
Oh,
where it maps
okay.
everything in L intersect E to itself. And since all of K is contained in L intersect E,
yes.
anything that fixes L intersect E must necessarily fix K.
But what fixes K will not necessarily fix.
Hence, phi in this has to also be a phi in that.
Right. Okay.
Okay,
I don't know.
really making me two of you are really making me question myself there. It's good, because if that didn't happen, then the rest of this proof kind of falls apart. So this is a subgroup of that. And what do we know about the Galois group of L over K? What did we assume from the start about that group?
Solvable.
It's solvable. What do we know about subgroups of solvable groups, Eleanor?
They're also solvable.
What do we know about things that are isomorphic to subgroups of solvable groups,
They're
Eleanor?
also solvable.
Yeah,
Wasn't that if it was a normal subgroup?
it's normal.
But we said that it divides.
Oh,
We didn't
Fine.
actually say it was normal.
Fine, whatever. If that's a subgroup for that and that, we know then that the Galois group of M over E is solvable.
What requires being a null subgroup?
The subgroup of solvable is solvable.
Yeah.
normal because it seems like you would get like things where go to the whole set and anything that's gonna
Actually,
fit.
does this have to be normal? No, not a question. I want to say it does by like the second isomorphism theorem consequence or something. Even if it doesn't, subgroup of solvable group is still solvable, works for non-normal subgroups, it's just that we only proved it in the normal case. So, it turns out this. Think about it. So this thing's solvable. So this thing has a tower of subgroups. How am I doing now? With subgroup tower. Starts off with the identity, which is equal to G naught, which is a normal subgroup of G1, which is a normal subgroup of which is a normal subgroup of G sub n equals the whole enchilada. With G sub I plus 1 mod G sub I abelian for each I. Sounds good? That's just from definition of solvability for the Galois group of M over E. So now, Emily Rose, now we're going to use our Galois correspondence to say, by the fundamental theorem of Galois theory, which we haven't even technically seen yet,
Varsity.
we can similarly get a sequence of subfields where K is contained in E. We're going to start at E on the bottom here, where E is equal to our, I don't know, we're going to call it some M sub R, which is contained in some M sub R minus 1, which is contained in which is contained in M naught equal to M of subfields of M. And I'll start with the next column. With each of these are the corresponding fixed field of something up here. So in other words, with the Galois group of each M over M sub I is equal to G sub I.
Is this E the same E?
E,
Yeah.
E here being the E that's at the bottom of this Galois extension. That's the base field in this Galois extension of M over E. So K is so the tower really starts at K. I just have K as starts at E, excuse me. I just have K as a subfield of, just to kind of remind us. But we get this tower of subfields that starts at E, works its way up to M. And the cool thing about the Galois correspondence is it's going to tell us that the Galois group of M over the corresponding M sub I here is actually equal to G sub I for each I, with the Galois group of M sub I over M sub I plus 1, each of these corresponding Galois groups is going to be isomorphic to G sub I plus 1 mod G sub I. Boom. Big result. Technically, you all don't know why this is true. This kind of follows from the fundamental theorem of Galois theory, which I promise we're going to come back to probably either Thursday or Tuesday, next Tuesday. But definitely one of those two. But Dr. Gerstle, why is this written in decreasing order and this is written in increasing order? Well, if you recall, when we did our Galois correspondence example, and what I hope you all did in the homework, one of your lattices has to be flipped upside down in order to get that nice correspondence. This one being in reverse order accounts for the fact that the corresponding lattice needs to be flipped upside down in order to get there. So that's why this one's starting at M sub R and working its way to M naught, and not starting at M naught and working its way down up to M sub R. Is just because of the kind of flip-floppy nature of the Galois correspondence.
Aren't the R's necessarily the same as n?
Let's see. Yeah, if we're starting at E, it does. You're right, it does. Now for, I'm not gonna have time to finish this. Do y'all mind staying a couple minutes after, or should I?
Today of all days, yes, because I have to be back by 1 to take a test.
Okay, fine. This is a good stopping point then. Jonah.
How do we know that it's got the double group of M to E is
M over E is isomorphic to the Galois group of L over L intersect E? We don't. That's a result from the book that we never discussed. Well, we know because there is reason to prove that, and it's somewhat similar to the second isomorphism theorem. Why that is, I say somewhat similar, and that it reminded Andrew and it reminded me of the second isomorphism theorem when we saw it. But there's details in there that would still need to be proven, and if we wanted to split this whole.
What? Is that like unity? Like that?
Basically, what ends up happening is we use the lemma that I erased to get the result we wanted. It's done.
But this switch
End of
is-
video. Finally,